overview of reinforcement learning. And the title actually, which we put out there, was with TensorFlow Agents. But in this talk, I would de-emphasize a little bit of the with TensorFlow agent, as it is only nothing more than a tool to implement these ideas. And it's the idea that matter, and that's really the meat of what the conversation tonight will be about. And how do we think about learning with uncertainty? And I like the way Alian introduced this topic. The talk is on machine learning. Well, that is true, but reinforcement learning has a different slant from how we would think of the other ideas of learning in an instructive manner. Now we still have a learner, or we still have a teacher of some sort in a reinforcement learning paradigm. But the difference here is that when you do reinforcement learning, you are learning via interaction. So you have an agent, this could be an abstract agent, that is interacting in an environment. And this environment is, we assume that the dynamics of this environment is complex enough, and we cannot know it entirely. So we can say that the environment is stochastic. But then we need to learn how to make certain actions that are optimal, or as we will soon see, that are close enough, which we call near optimal as the agent interacts with this environment. So the agent is learning, we are learning via evaluation, evaluating actions in a bid. So the big idea is to understand which are the best set of actions I can take in the changing dynamics or states of the environment in which I am interacting in. Whereas in machine learning, you have it's learning by instruction. In the more perverse case, which is called the supervised machine learning, the teacher is giving guidance in a sense. So it is guided learning. You have a sample of the target population you're trying to learn the dynamics about. And then from that sample, you have a desired target, the objective you want to learn, and then the rest of the story of ML, of supervised ML, are the ways and means in which we can build an approximate solution so that we can generalize when we take the model, in that case, or the classifier, to an out of sample use case. So, but in reinforcement, we do not have these pre-labeled samples, but we are choosing actions. So that's really the big idea, the shift in how we think about it. But we'll talk about that more as we go through the talk. But I shall start by, I think I've gone through a bunch of slides already. But again, I think this kind of summarizes it, that reinforcement learning is the idea of learning from interaction with an environment. And it builds a lot historically from the theories of what we call trial and error learning and adaptive control. So researchers who have worked in learning, optimal decisions in dynamical systems or the rest, you see those ideas spill over in the historical background to RL. So the goal of the agent is, how do I maximize rewards? So rewards is a signal that you get from the environment that kind of steers the agent towards the desired goal. So how can these rewards be maximized? Just as we think of in a naive way, we could think of a child trying to learn, and there's something that is immediately, an event that is immediately painful could be a penalty. Whereas an outcome that achieves some objective, probably the objective of the child is to get candy from a pot. a cup or something or whatever. Now, if the child gets an outcome from the environment that moves it towards its goal, and how the child interprets what is favorable or not can be seen as a favorable outcome. But in any case, whether it's a penalty or what unfavorable or unfavorable outcome, we generally call it reward. And so there's a reward function of some sort, or a reward signal of some sort. So this whole interaction is in what we call the RL feedback loop. So this is an agent interacting with an environment, and the agent is receiving a response from the environment, which is the reward signal. And in the reinforcement case, we are also, which we'll talk about shortly, we're also receiving the new state of the environment. So if we take from the left-hand side, let's assume that we have an agent in an environment. The agent has, through some means, chosen an action as it interacts with that environment. Now, what the agent gets back from the environment is the new state that has resulted from the action the agent took, and a reward signal of the action that was taken in the previous time step. So we can see that as a general reinforcement learning framework. Now, in keeping with the idea of a goal-directed learning, the agents are not told what actions to take up front. They have to evaluate and figure out what are the best options to take. So the agent has to discover the actions that provide ultimately the most rewards in terms of what the goal or the objective is. And this is very complex, as we will see. There are a bunch of considerations that we have to think about in trying to design this sort of goal-directed agent learning via interaction. I will skip over these slides because in the introduction, I think I went, Alien gave a good segue, and I built on that to speak about the difference between reinforcement learning and supervised learning. But then I will also talk about the difference between reinforcement learning and unsupervised learning. In an unsupervised machine learning problem, you are trying to find the structure in unlabeled data. But in reinforcement learning, as we just explained previously, we are seeking to maximize a reward signal as opposed to finding a hidden structure or a hidden pattern. So but what they have in terms of the similarities is that you are still relying on examples from the environment, which in an unsupervised case, it could be data sets you have. And in a reinforcement learning case is the observations, is the state, what we observe from the state of the environment. So a central challenge in the reinforcement learning framework, or I would say, reinforcement learning framework is how do we know or go about, how do we engage in the process of learning the best actions to take for a particular state or setting of the environment? If we have taken an action before, we can have an idea from experience what type of reward signal that action gave us. However, for actions we have not explored, we don't know. So we can take an action that we find immediately desirable and say, you know what, I'll just take this action all the time. Now, let me use an analogy that you come to the city of Calgary, I stay in Calgary, and you want to try out restaurants for dinner. and you stumble into a Nigerian restaurant. Well, I am Nigerian. You stumble into a Nigerian restaurant, and boy, the food is amazing. You say, you know what? For the next 1 month in Calgary, I'm going to come here. But you see, what you're doing is that you are exploiting a choice. You're exploiting an action that you find desirable. But however, you have not gone into the Mexican restaurants or the Indian restaurants. And this may give you a better sense of fulfillment or a stronger reward signal, but you don't know because you have not explored it. So these are the issues in how do we take advantage of information we already know to make actions, balancing it with exploring from actions that we don't know what the outcomes may be. And this is the trade-off that an agent needs to make in learning with uncertainty, the trade-off of exploration and exploitation. Now, we do know that a greedy agent, now greedy in computational, well within the computational literature, is an agent that totally exploits or will take advantage of an action it already knows what the reward is, and it is sufficiently desirable. So just a purely greedy agent has shown, at least from a theoretical perspective, and it does hold empirically, to be suboptimal and will not maximize rewards in the long run. So how can we, so balancing exploration and exploitation creates a better, an agent with a higher, in terms of how it maximizes reward, it does it significantly, or an order of magnitude better. So that's a key thing to put in the mind as when we think of reinforcement learning, balancing exploration and exploitation. Now, the mathematical formulation of an RL framework is what is called the finite Markov decision process, or in short, MDP stands for Markov decision processes. And it is a mathematical formulation that defines how an agent will make this sequential decision making as it transits from one state to another in interacting with the environment. And a couple of concepts we see in the MDP formulation is the idea of a state space. Now, the state space, I'll try to keep it in a restrictive sense, is I would call it the various settings or dynamics of the environment. Now, this state space could be very restrictive. Say if you're playing, it can quickly grow exponentially. But say you have to, a very naive or trivial is a coin toss, and you have two states, heads or tails. Now, but if you take that out, you could have, as you know, the state space you can see how the state space can easily grow exponentially. Now, the action space is the set of actions that the agent can take as it interacts, as it makes choices in the environment. And the reward function captures the reward dynamics in terms of the signal in which the environment returns. Is a function of the environment that informs the agent on the desirability of an action or the desirability of staying in a particular state or making a particular action in a particular state. And then we shall talk about discount factor as we go on. And I think using this formulation of an MDP, we expanded the diagram of the RL framework, where at a particular time instance T, an agent has input, which is the current state I wouldn't say response. Let me put a step, go one step back. In an initial setting, the environment, this agent is able to perceive the state of an environment. The agent takes an action. Let's not worry how it makes a choice on the action, but the agent makes an action in that environment, and it gets at the next time instance or the next time step, it gets a new environment dynamics, so the state has changed, and then it gets the response from taking an action at step T. It gets a response, what is called RT plus 1, for which the agent works with this information to update, to inform how the agent will make the next action as it interacts with the environment. Okay, so we are building up, and I'm carefully putting some of the other fine detail would come later, but this is, even if we live with anything in this 1R, is to have an appreciation of the reinforcement learning setup, and hopefully see avenues where this can be applied to various problems. So the agent and the environment work together, which we call the agent environments interface at discrete time steps. Now, it's more or less a conceptual formulation, but then that means one setting changes into another. So that's what we mean by discrete time steps. Now, this slide, I think, demonstrates what we earlier discussed about when an agent takes an action, it receives the reward, an outcome from its action, and the new state, for which it now makes the decision on what new action to take in that new state. So the sequence here, or the trajectory, is that the reward of the previous state somehow has an impact on the action that the agent will take in the next state. Okay, so the goal of the agent is to maximize the expected sum of rewards, and this is called the return. So the return in RL parlance is the sum of future rewards. Okay, so while in a particular state, what is the sum of future reward? That's called the return. The next thing I would call component, really, for an MDP is the idea of episodic and continuing tasks. So an episode is where the agent environment interaction splits into natural sequences. So for example, you are playing a game of Pong. We can say that an episode ends when the game is over. So probably the agent has scored a point, or the agent has reached a particular points total. So that interaction is episodic. Now, the other is a continuing task, where the agent environment interaction continues without limit. So, but then if we think about continuing tasks, we have a problem in defining return, because you remember we said that T is the final time step. But what happens when T is infinite? We need to think about how we shall define return. And this brings us to the idea of discounted return. If you remember, when we introduced some of the components of an MDP, we had the value gamma, which we call the discount factor. And I said that we shall consider it. So this is where it turns up again. Now, the gamma, the symbol here, is what is known as the discount rate. And it's a number bounded between 0 and 1. And it is the rate for which we discount future rewards. In other words, when we talk about discounting future rewards, we would say, how shall we weigh? How will I put it now? How shall we weigh the in calculating the return? What weight do we put on immediate rewards as opposed to long-term rewards. So that's what the discounting means there. So when, let me see if I have that. Okay, this is what I'm looking for. Now, if gamma is 0, then the agent would be a completely myopic agent. It would only learn about actions that produce an immediate reward. Now, this might not be the best, even from our own experience as natural agents. So if you want to succeed in a class, you have to do a task that maybe for most people be considered undesirable, and that is sitting to study long hours in hope of a long-term reward. But perhaps watching a soccer match or playing video games may be more desirable in the immediate, but may be detrimental in terms of maximizing future or long-term rewards. So whereas if lambda is equals to 1, so the agent will purely evaluate each of his actions based on the sum total of all its future rewards. So that is how we shall think of return. We'll think of it in terms of discounted return. How much weight do we place on immediate rewards? And this helps, and this from a theoretical perspective, we shall not go into, to see how you can convert a continuing task to look more like an episodic task. Okay, now the other key frame and pillar of the reinforcement learning framework is the idea of policies and value functions. So remember we said that the Markov decision process is a formulation in terms of how an agent will make actions in an environment and will obtain rewards. Now, in doing so, we would think of the idea of desirability of a state or desirability of an action. Now, when an agent perceives a state, it takes an action that will affect the new state that the agent perceives or receives from the environment. So the question becomes, how do we know that we are in a good state? How desirable is it for the agent to be in a particular state? Those are things we would like to know. Also, we would like to know how desirable it is for an agent to take a particular action in a particular state. So these are things, questions that we would like to compute, we would like to evaluate as we make these decisions. So, okay, I think I'll just read out what I put here. What is the probability an agent will select a specific action? That is the desirability of an agent choosing an action in a particular state. And this is critical because the action will affect the rewards. So knowing the goodness of an action in a given state is something that the agent would like to be able to figure out. So how can the agent do that? So, and we will come back to this question of desirability when we talk of value functions. Now, but let us talk about, let's talk about a policy. Now, a policy is a function that maps the state to the probabilities of choosing an action from that state. So, so it maps a given state, a given state to the probability of an agent selecting a possible action from the state. So ideally, what we are learning is a policy. And we want to learn, we are asking the question, what is the optimal policy? And we shall touch briefly what we mean by optimal policy. So an agent will select a specific action in a given state based on some probability, right? So that mapping of action probabilities to state is what we call the policy. And this is denoted by the symbol pi. Again, formally, we say that an agent follows a policy. Now, in other words, we can also say that at a given time, T, under a policy, what is the probability of taking an action in a given state? And that's what this mathematical expression here, this conditional expression, means. The probability of selecting an action given a state. What's the policy? So following a policy. Now, we said we're gonna come back to value function, which is knowing the how good it is for an agent to be in a particular state. So value functions, we'll talk about what we call the state value function and an action value function. So the value function would help us to estimate how good is it, or the state value function will help us to estimate how good is it for an agent to be in a given state. And the action value is how good is it for an agent to perform a given action in a given state. So I'm looking at the time, but I think we are getting close. So I will skip a little bit of the math in terms of describing it, but what I would mention here is that the value function, we are trying to see the expectation of the return, and the return we talked about is the sum of rewards. How much rewards, given that an agent is in a particular state, or given a particular state. And then the action value is expectation of a return given that an action is taken in a state. And that's the difference between a state value function and an action value function. The action value function is particularly important because this is also referred to as the Q function. Now, we will then introduce the idea of Q value. So we'll think of Q function as a table of some sort that contains Q values. So remember, action value is the goodness of taking an action in a particular state. So you want to think of a Q function of a table of states to actions, and then have a way of weighting how good is it to perform an action in a state. So it is the output from the function for a given state action pair. So this can then be used to estimate. So really, the reinforcement learning algorithms, which we will talk about a particularly important algorithm called the we'll talk about a particularly important algorithm, which is called the Q-learning algorithm. So it would estimate value functions for which we will use to determine the best policy for the agent. Okay. Now I know we mentioned that the agent follows a policy, and it would be desirable or preferred to follow an optimal policy. So we can define optimal policy as for all. Okay, let me take a look at this. So for all candidate policy, a policy that is better or at least the same as all the other policies is called the optimal policy. And we remember that a policy is a mapping from the state to the probabilities of taking an action in that state. And the optimal policy is one for which there's following from the starting state and all the next sequence of states that the expected return is greater. Okay. Then having spoke about the optimal policy, we will then we will speak, I will skip this slide. Okay, I will mention that. We'll speak about the optimal state value function and the optimal action value function. And we'll recall that a state value function is the desirability of an agent being in a particular state. So the optimal value function would say, given the policy, what is the maximum? What is the best, given the policy, following the policy, what is the highest given a particular state? So it's the largest expected return achievable by any policy in a state. All right. Then for the optimal action value, remember we talked about action value is the desirability of taking an action in a state, which is called the Q, also called a Q function. So Q star gives the largest expected return that is achievable by a policy for each possible state action pair. Now, this is the core computational mechanism in how an agent evaluates or agent tries to find what the optimal policy is. And that's called the idea of a Bellman optimality equation. Now you will see that it must satisfy the equation that the Q star SA is the Q, or in this case, the optimal action values function, in that we want to find the expectation of the return, and then we add, I think I should move to, no, I don't know if I want to stay here too much, but typically this is an iterative algorithm, but the game here is that moving to the next, we want to find the best return, and for which in the next state, we also want to find the maximum Q value that is discounted, the discounted return of subsequent action for subsequent Q values or subsequent action values that is discounted for sure, more so in an episodic in a non-episodic environment. But we will see the Bellman optimality equation come to life in how we do that computation. We have an example of that in the slide. Okay, now having said that, computing this by hand, we could see how this can immediately become very tedious, especially if you have large states and a appreciably large number of actions. So given a state, you want to compute the Q value, and then you want to use that information to make a choice on desirability and the like. So it can be very heady in computing it. So we have to make use of approximate solutions. Now, in RL literature, you would see they will talk about three classes. Talk about the dynamic programming method, the Monte Carlo method, and temporal difference. So I won't go into some of those things, but just to say it in case people want to take this home and learn more about this idea of learning. In a dynamic programming formulation, you can find, in theory, the optimal policy. But doing so is computationally expensive and potentially intractable, especially for large state action spaces. And the other is Monte Carlo, that involves some sort of simulation. And it has its own drawback, but it can help you make a near optimal solution, but you don't need to know the complete model of the environment. That's why it's probably called, I guess, the model-free learning. But temporal difference is we want to use some of these interesting methods that kind of combines nice things from dynamic programming, nice things from Monte Carlo to build an approximate solution that will give us to an approximately good policy that is close enough to the optimal policy. All right. So Q-learning is an algorithm to solve or to approximate the optimal policy in a in an MDP or in a Markov decision processes. Okay, I think I've talked about it. It's an algorithm for learning the optimal Q values. Yeah. Okay. Now, given the Bellman optimality equation, which we presented previously, where you have an expected value of the return for a particular state plus the discounted optimal Q values of the future states. We want to iteratively update the Q value in Q-learning algorithm. We want to iteratively update the Q values for each state action pair. And we want to do that using the Bellman equation until we can converge to the optimal Q value, or we can approximate, in a sense, the optimal Q value. In practice, I will use the word approximate. And that process is called value iteration. Pardon me. Okay, we shall do this with an example. We have an example here called a foraging agent. And in this example, you see a fox will want to get pieces of meat. And the fox will also want to avoid the hunter. And we can look at the various spaces in the grid, cells of the grid, as states of this environment or of this world. So, okay. So I would, if the fox gets into cell 8, going from left to right, it will get to +1. If it gets to the cell that has 2 pieces of meat, it goes to, will have a reward of +2. If it's 3, it will be +3. But if the fox encounters the hunter, it will get a reward of -5. Now, when the fox gets a reward, sorry, when the fox encounters the hunter, the game ends. Also, when the fox gets the maximum number of rewards possible in this world, we should also end an episode. So that is the setup of the environment and an agent, which is the fox interacting with this environment. Okay, now you see an example of a Q table that has Q values. And we talked of the state action pair. So here we see the state as the horizontal entries are the states and the vertical are the actions. So initially we assign them to 0, but there are other methods out there in the literature for how you may want to assign these initial Q values. We could start with an initial optimistic value, but we shall not talk about all of this. Now, for the basic pillars that we have discussed, you can see various ways from in the literature of how this can be tweaked in one way or the other, to all in the bid to find what is that near optimal policy for a sufficiently complex problem. Okay. Now, we want to define, I think I would come to this idea of an epsilon greedy strategy. I will come back to this slide because just saying it here, I want to say a few more things before I talk about this idea of epsilon greedy. But in any case, what you should take from here is that in the final analysis, as we do the computation, we want to have what we call an exploration rate. And we will see that when we look at the code sample. So if the probability is more than the exploration rate, the agent will exploit from the actions it already knows about. If it is less than that, the agent would explore. So, and as the episodes proceed, as the agent keeps playing this game over and over, we would gradually decay, or in this sense, we would make the But decay in this sense is that we'll make the agent become more greedy so that over time, when we have learned sufficiently the dynamics of the environment, the agent begins to exploit the information it already has. So for example, I will use it may not be reading map exactly, but as we grow older, we are averse to, we may be typically, not everybody, you've seen people who are really old exploring new things, but there's a tendency to be averse to exploring new things. The older you get in life, you want to stay with the things that are tried, tested, and true. You know what outcomes to get, and you are okay with that. So you want to think of it that way, why we would decay gradually for every episode. So this exploration rate will govern whether an agent will exploit or explore at every step when they try to make an action in a particular state. Okay. Now, the very first action is chosen randomly because we don't know anything about the environment. The first action is chosen randomly via exploration. And because our exploration rate is set to 1 initially. But then let us assume that the fox goes up. And I should have mentioned that now. If the fox is in an empty cell where there is no food and there's no hunter, it gets a penalty. I mean, it gets a reward of -1. Right? Okay. So let's assume the agent moves up, it gets a reward of -1. Now we need to update the Q value in the Q table. And we update the Q values in the Q table using the Bellman equation. Now, the goal is that over time, we will approach what we call the Bellman optimality as we compare the loss between the Q value and the optimal value and the optimal Q value. Now, this will be understood better in the subsequent slides, but I will come back to this when I speak on that. Again, another thing I will mention is the learning rate, and which we can think of it of how quickly would an agent change or update the Q value in the Q table. So especially how much or how quickly will an agent change or update the Q value in the Q table? If you have a high learning rate, the agent will more quickly adopt or adjust the new Q value as opposed to a lower learning rate. So those are heuristics that the model designer will have to take into consideration. Okay, so in calculating the Q value, given the Bellman equation, we would say that the old Q value will be multiplied by 1 minus the learning rate plus the learning rate multiplied by the learned value. And this is what we use to update the Q value of a particular state action. Now, in the case where we had the initial Q value for when we moved up, the initial Q value there in that cell was 0, because that is how we initialize the Q table. And let's assume that our learning rate is 0.7. So we have 1 minus 0.7 times the old Q value, which is 0, plus 0.7, the learning rate, multiplied by the reward of the next state, t plus 1, which moving up is -1. Okay, plus the discount factor here is 0.99 plus this equation, which is the maximum Q values for the new state. Now we will zero in on this in the next slide. So working it through this way, we understand the Bellman optimality equation more better, or better, well, better. Okay, now this term, the max of the Q value for the new state is, given that we are in the new state, the actions we can take in that new state. So let me go back to this slide. Okay, given we are in, so we moved up, we are in this state. The actions we can take here is that we can go up, we can go left, and we can go down. So we want to know the desirability of taking an action. Which action is more desirable given that we are in cell 16, counting from the top. Counting from the top left, given that we're in cell 16. Cell 12, sorry. Okay. So if you go to the left, sorry, going to the left, yeah, okay, of course, that is correct. Now, going to the, let me start with going up. Going up, we have a reward of 1. Going to the left and going down, we have rewards of, that's a mistake, that's why I got confused. We have reward of, no, not reward, sorry now. Going up, we have a, let me come to this table. Yeah, in this assigned reward for each state, okay? Okay, we have -1 when it's empty. That's what I was looking for. So going to the, this is not about reward. Give me 1 second, I'm mixing things up in my mind. Okay, I get it now. Now, when you go to the left, the Q value there is 0. If you go up, you have 1. Or the reward is 1, sorry. And if you go down, I think this should be -1. This is what's confusing me. This should be -1, for which the maximum of it is 1. So I need to edit this slide. Okay. And that is correct. So go to the, going to the left, -1, going up, 1, going down, -1. So in this case, the maximum Q value, given that you are in the new state, is 1. So 1 goes into this equation. And you see how this, so when you compute all of this, you have the result of -0.007. Then you update your Q table. And then you roll a dice using the exploration rate, and you know whether you should explore or exploit in choosing the next action. So you are updating your Q values in the Q table as you continue to interact. So you can see how over time, by degrading the exploration rate and updating these Q tables, we can find out, even we can know which actions are more desirable and which we can exploit better in the long run. And we see how we use the Bellman equation to compute what these Q values are iteratively using the Q learning algorithm. Okay. So we will store this new Q value in the Q table, and it will happen for each time step until termination in each episode. And then, in a sense, once the Q function converges to an optimal Q, to the optimal Q function, but you cannot know this. But theoretically, it has shown that the Q function would come near enough, given that you run the game over multiple episodes, would approximate the optimal Q function. So we have an approximately optimal policy. Okay, let us come to code. So like I explained, I know we are at the end, but this is not so much of the TF agent, it's about the ideas that makes working with TF agent a very convenient and nice tool for building reinforcement learning agents. Okay, this is some bunch of things, packages to install the TF agents, and just a bunch of other things. I would move across this much more quickly. And then we want to install we want to call the TF agent environment. Now, TF agent comes with some environments that enables you to rapidly evaluate the performance of your agent and to see how much it learns, how well it can learn in some of these default environments. But TF agent exposes abstractions where you can code your own environment and you can expose the dynamics of that environment, which is the states, the actions, and all of that, and the rewards. And you can use those custom environments you can wrap TF agents across your coded custom environments for the learning setup you're trying to construct. Okay, now we will use a popular environment from the library called the Frozen Game, or Frozen Lake, sorry. Frozen Lake game. So here we have an explorer trying to avoid holes by standing on the areas of the lake that are frozen. And the goal state is to get to the bottom right of the cell for which the episode ends. If the explorer falls into any of these holes in the lake, the game also terminates. So this is the state, and the actions in the environment is to go up, down, left, or right. So we have 4 actions, and these are the states of the environment, all 16 of them. Okay, so we create the environment. Here we call it Frozen Lake, and then we need to create the Q table. So remember, the Q table is a state action pair. So we want to know the number of actions in line 5 and the number of states, and then we use that to create the Q table. So you can see how the Q table looks like initialized to zeros. Okay. And the next thing we will configure some of our parameters. What are the number of episodes? How long should you run this? So we are going to have 30,000 episodes. Now an episode would end either the goal state is reached or the agent falls into a hole. And we'll keep playing the game 30,000 times, and then we stop. We stop the algorithm. And then the learning rate here is 0.1. And the maximum number of steps per episode, that is, if the episode does not end naturally, after 100 steps, moving around the environment, end the game and start a new episode. Reset the environment, start a new episode. And then the discount rate in how it discounts future rewards is set to 0.99. Then we should talk about some of the exploration parameters. We will set the exploration rate is set to 1. Of course, this would be gradually. Give me a second. Yeah, this will be gradually degraded as the game goes on. Now, because we want the agent to begin to exploit, as we have learned, gain information of the environment. Okay, then the maximum epsilon, which is the exploration probability at the start, of course, that is 1. And we will degrade up until 0.01 and will not degrade below that. Because if we do so, we would eventually degenerate to a totally greedy agent. But we still want to leave some form of exploration. Okay, and then the decay rate is how much are we decaying epsilon over time, and that is set to 0.01. Okay, so this is the meat of the Q-line algorithm. So we have a list of rewards, and we have a double for loop that would say we are going to, for each, the first outer for loop contains the code, what will go on in a particular episode, and the inner for loop is the activities that will occur for this step as the agent interacts in that episode, in the environment. So when a new episode starts, reset the environment, and we set a couple of parameters, set the step to 0, set done to false. We'll get to know more about this, set the total rewards to 0. And for each step in the episode, we want to find a uniform random number between 0 and 1 that will let us know if we should explore or exploit. If this number in line 18, if it is greater than the exploration rate, then we will exploit using information in the Q table. If it is less than the exploration rate, then we will explore. And we'll take an action from randomly from the action space. Okay, so when we take an action, it's stored in the variable action. Now we also observe the outcome of that's the new state, the outcome state, and the reward. So we're going to store that in the new state reward variables. Now done will only change to true when the episode is over. You remember the episode ends when the explorer falls in the hole or reaches the goal. And this will store some information about the state. So how we do it, we call the environment and we take a step and pass the action to the step we will take in that environment. Then we update the Q table. So this computes the Bellman equation we used earlier, that for a state action, we want to update it, given the learning rate, and we're going to use the reward, the discount factor, the reward plus discount factor times the maximum of the Q tables for that, the Q table for the particular new state. And then we will subtract that from what we have already in that state. So this is saying what is the desirability of taking an action while I'm in this state, and this is already the desirability of being in that state for the action we already took. Okay, and then we update the total rewards. We will have to keep this count of the total rewards. And we update the state. Sorry. Yeah, and then we'll update the state. And we go to the next step in the episode until done in line 7 turns to true. So we have this code in here in the next slide, and if done is equals to true, then that episode is over, break, and we go to the next episode. But if done is not equals to true and we have exhausted the number of steps, reset the game and start a new episode. And another important line of code for every episode is that for every new episode, you want to reduce the exploration rate over time. And then we see the score of the rewards over time, and we'll print the Q table. And we can see how the Q table, doing this long enough, can be used to find better actions in a state. So I would leave, in the interest of time, this is just, now you can then use the Q table you have learned to play the game. And you will see that the Explorer, after after about 15 steps in the first episode, really, the explorer is already learning how to get to the goal state. So this is the kind of things, we can begin to think of the kind of use cases in which we can construct. Once you can construct this agent environment interaction and learning a goal via interaction, then that problem can be cast in a reinforcement learning framework. And just in case you want to play with the code, this code was adapted from this GitHub repository. And I think it's a good, well-written, well-documented code. You would like to go and play around with it there. Now, I want to end by saying that Q-learning is the framework for which we have the so-called QDN, the Q deep neural net. But when you're using deep neural network to learn the Q values, what you're doing is that you are now estimating the Q values using any of the deep neural architectures, a convolutional network or the like. Now, assuming you want to learn how to play a game like the Atari games or the chess games, you have video scenes and the states of the environment are different batches of pixels. You could then see how Q-learning could use an approximator that we know is optimized for learning images, such as the convolutional neural network, as the algorithm for learning the Q values. So, but I guess I just wanted to say that this is the foundation of how you can think, of how you can explode, make this idea even more powerful for complex problems using deep neural architectures in the field that is now called deep reinforcement learning. I hope that by this 1 hour lecture, we can have a taste, in a sense, of reinforcement learning, and our minds can be engaged to see ways in which this can be applied into different problems that we care about. Thank you very much for your time and for listening. I'll hand over to you.
Thank you. Thanks a lot. That was great, because I know that whenever we get into AI, I tend to be scared about all of the equations and stuff. But your examples were perfect to really illustrate how it works. And once we see the examples with the fox and everything, I was like, oh yeah, now I get everything he talked about. So that was perfect. And we have a bunch of questions from the attendants. The first one is, so you have experience in AI, machine learning, reinforcement learning, and the question is, if someone who's already a developer, who knows about code, who knows about, and basically fluent with a computer, wants to get into that domain and learn the basics, do you have a resource, a website that you know about that is very beginner friendly, I would say, to get started?
Well, someone who already knows how to code and the rest, there are a ton of materials out there. Well, I will be extremely biased in suggesting a resource. I actually wrote a book 2 years ago, 2019. That book was published November, I suppose, titled Building Machine Learning and Deep Learning Models on Google Cloud Platform. Okay. Now, that book is, in my mind, I wrote it for a question like this. So when I wrote that book, I thought about my students. I used to teach as a lecturer in Nigeria. I thought about my students, and if you don't mind, I would stop sharing, and there's something I want to say about that. And again, it's biased, but I would think it would spare you a lot of the heavy stuff, and I think it's a springboard to get into some of the hardcore stuff and really enjoy it, because this field is lovely, but for many, the math or the presentation may not let them see the beauty in it. So I think I want to share this tab. I hope I'm in the right tab.
I found the link to to your book on Amazon.
Okay. So in particular, the part I like a lot about this is when we talk about this is part 2. We have what is called programming foundations for data science, which we had just enough to be dangerous for Python, NumPy, Pandas. These are the basic libraries you want to know about.
Okay.
And then when we talk of introducing machine learning, then we introduced you to tools like scikit-learn. And then we came into within the purview of actually building these algorithms. So we see them come to life, and then we went all the way to deep neural networks and talked about TensorFlow, and went through things really in a didactic, systematic manner. I think this book would be a very good tool for one who is already a programmer and you want to build AI powered, where I don't like to use the word AI. AI is much broader, but you want to build ML powered applications. This skill will be increasingly, in my opinion, an increasingly valuable tool for developers, because a lot of these methods are packaged and we are seeing it being mainstreamed into it's becoming first class, mainstreamed into the software development ecosystems. So it's something I would think, and I think that's a good place to, it's good to pivot to that at this time.
Okay.
Yeah.
Perfect. Thank you. And the other question we have is actually in the chat and in the Q&A. It's a longer one, so you probably want to read it because if I read it, then it's a pretty long question, but a very good one actually.
Is it by Jason?
Yeah, the question from Jason. Yeah.
Okay. I would like to know whether the law of diminishing marginal returns is ever modeled in RL. For example, okay, first of all, the law of diminishing marginal returns, the way I understand that from economics is that in making a decision, you forfeit something for the decisions you did not make. Jason, I hope I'm saying that right the way you want to think about it. Okay. So for example, if I eat one ice cream cone, my reward might be 100 enjoyment units. But if I eat 10 of the same ice cream cone quickly in a row, my reward for the 10s, the same stimulus from the environment, might only be 10 enjoyable units. The concept of discounted future is similar, but not the same. That's true. A week from now, if I eat that ice cream cone again, my reward might be back at 100 enjoyment units, even though it's further in the future. And this is a very good question. And I want to say that this law of diminishing marginal returns is or can be modeled in our environment just by when we talked about the framework and the dynamics. You see that you can inject a lot of speciality and a lot of bells and whistles and expand this framework. So it is just a framework, but it can be made very expressive. And if you think of some of the other algorithms out there and methods, you see how researchers have used the first principles really in terms of learning from interaction and how you can take advantage of the words and how you can make you can make decisions based on that and the kind of goal you want to achieve long term. You see how it's interesting in the literature to see how researchers use this to build various expressions, but they still do the very same idea of learning a policy that is near optimal that will enable you to be successful in a given environment of interaction. And I believe this problem is similar to how you have a different data set in a supervised machine learning case. And we know in supervised machine learning, we have the idea of no free hunch. So there is, I suppose, a no free hunch theorem, even for RL, where you have to, the use case helps you think about how you want to model it to capture. So this is a viable challenge, and it does account for that. And I think in a sense, this is some of the information about what we want to talk about, but not, I don't think it's not directly, but you can see traces of it. even in the idea of, it's a more skinny version called contextual bandits. And there are also other RL algorithms out there apart from Q-learning. So for sure, RL takes a can model law of diminishing marginal returns. I don't know if I can think of an algorithm now that does this, but I can put my bet that it is in the research papers. We'll find something that answers to this kind of interesting use case. But thank you, Jason. That's a very thoughtful question. Yeah.
Perfect. Thanks a lot for your answer. And looking at the Q&A, I don't see any other questions. So if anyone wants to ask something, we can give you a few more seconds if you want. And otherwise, we might call it a day for today.
Yeah. But I want to thank you, Alan, again, and the GDG Sacramento team. Thank you for having me. I am very grateful and
Well,
happy.
thanks a lot for taking the time and doing this talk for us. I know it's a lot of work to prepare for this talk, so your time was appreciated, and you made it easier to understand all of these concepts. So that was a great performance, because I know that all of these concepts are really complex, difficult to explain, but your examples were perfect. So thanks a lot for coming to GDG Sacramento tonight. Thanks everyone for attending. We will be posting the talk on YouTube shortly, probably by tomorrow or this weekend. And yeah, thanks everybody. Have a very good night and see you next time.
Okay, bye-bye.
Thanks. Bye everyone.